Last month, a Chinese company everyone started calling Chip X claimed it built a new optical quantum chip, allegedly 1,000 times faster than Nvidia GPUs for processing AI workloads. Before the conversation could cool down, this month brought another announcement from Chinese scientists. Shanghai Jiaotong University and Tsinghua University has allegedly developed a new series of photonic, light-based AI chips called LightGen, reporting that it could outperform Nvidia's A100 GPU by over 100 times in speed and efficiency at specific generative vision tasks, especially video production and image synthesis. The prototype results suggest 35,700 TOPS, 35,700 trillion neural operations per second, and 664 TOPS per watt, while only using a fraction of the energy a digital GPU normally demands for those same workloads. This wasn't framed as a benchmark rivalry. It's an architectural exit. Silicon overheats, so light rewrites the ceiling. If this architecture scales beyond prototype, the entire AI hardware map gets redrawn, and the countries restricting chips today may eventually be competing for access tomorrow. The future didn't move west, it refracted. To understand why this announcement resonates so deeply, we have to take a step back and look at what exactly the current AI compute stack looks like, and why it's become such a bottleneck. Right now, AI progress is driven by digital chips, especially GPUs. GPUs were originally built for graphics, shading, 3D rendering. Over time, their ability to do massively parallel math on demand made them perfect for neural networks, transformers, and deep learning. Nvidia's A100 GPU, for example, is one of the most ubiquitous compute engines in AI data centers because it was engineered to handle massively parallel AI math at high precision. It trains neural networks, runs transformer interference, executes programmable CUDA kernels, and stores massive tensors in a high-speed VRAM. That combination, flexibility, programmability, parallelism, memory bandwidth, is what made the A100 and its successors the backbone of AI clusters. But that backbone comes with costs that most people outside hardware engineering never think about. When you run AI at scale on GPUs, you don't just pay for the chip. You pay for the entire power and cooling infrastructure that chip demands. A single Nvidia A100 board pulls around 300 to 400 watts under stress. That's one board, one chip. Now scale that. A cluster of 10,000 A100 boards pulls 3.5 megawatts of continuous power.
A cluster of 100,000 boards pulls 35 megawatts. And that's not counting the extra power you have to lay down just to cool the heat those chips generate. That's the electrical footprint of a small city, all just to keep AI math running. And the reason data centers heat up isn't because the math is impossible. It's because billions of digital transistors switching at clock speed leak voltage, waste energy as resistive heat, and demand massive cooling budgets to keep temperatures stable. Cooling isn't optional. It's existential for silicon at scale. This is where photonics isn't just an upgrade to silicon. It's a completely different bet. Instead of electrons flowing through metal interconnects and transistors switching digitally at clock speed, photonic AI chips perform neural matrix math using photons traveling through optical waveguides. Photons don't leak voltage the way electrons do. They don't generate resistive heat when traveling through waveguides. Instead, they interfere, diffract, resonate, and shift in phase. And those behaviors can be engineered to execute analog matrix math incredibly efficiently if the chip is designed for that workload. The math literally happens through the physics of light behavior itself. That's the architecture, that's the physics, that's the shift. But there has always been a catch. For years, photonic chips have shown promise on specific recognition workloads, like image classification, low-light feature extraction, and convolution math for decision tasks. But those pipelines can tolerate patch-by-patch processing and lower precision. But photonic chips have historically struggled when the job gets harder, when you need coherent generation, not just recognition.
If a chip processes an image in tiny tiles and then stitches them back together, you lose quality and coherence. The outputs feel disjointed. That's why earlier photonic efforts were more curiosity than competition. They could do neat math, but they couldn't compete with silicon when the output had to be complete and seamless. This is exactly why LightGen stands out. The research team built LightGen not for simple recognition tasks, but for generative AI workloads in the vision family. Tasks like high-resolution image synthesis, 3D scene generation, style transfer, denoising, and short HD video frame production. These workloads are pushing GPUs harder than almost anything else because they require both massive parallel compute and large memory footprints. And when you scale them across clusters, the cost in electricity and cooling spirals rapidly upward. The difference with LightGen is its 3D stacked photonic neuron architecture. Instead of being flat, LightGen stacks more than 2 million photonic neurons vertically in layers, allowing it to compute entire semantic visual fields in a single optical generative loop without breaking the image and stitching it back together. That 3D stacking is key because it removes the fragmentation problem older photonic chips faced, a problem that wasn't about weak math, but about structural limitations. Think of it this way. Old photonic designs were like trying to paint a mural block by block and hoping the seams didn't show. LightGen is trying to paint the entire mural all at once, with light. But LightGen isn't the only intriguing optical chip emerging from recent research. Accel was developed at Tsinghua University. Unlike LightGen, Accel is not fully optical. It is a hybrid processor that combines photonic components with analog electric parts. In lab results, Accel delivered 4.6 petaflops, 4.6 quadrillion operations per second, while consuming extremely low power because it runs fixed preset analog neural math loops, not programmable kernels, not software execution, not transformer training, and not memory-heavy tensor storage. Its strength is in preset analog convolution math and latent optical transforms for recognition workloads. So let's be clear about the difference. Accel is hybrid photonic plus analog electronics. LightGen is fully optical. Both point in the same direction, light for math, electricity for orchestration, but neither is a universal programmable GPU replacement today. Now let's talk about the numbers, because that's where most people lose track. TOPS, tera operations per second, measures throughput for preset neural math loops, not digital floating point flops used in transformers. 35,700 TOPS means 35,700 trillion neural operations per second. 664 TOPS per watt means 664 neural operations per second for every watt of energy consumed. For context, Nvidia's A100 GPU delivers a few hundred TOPS under FP16 workloads, while pulling 300 to 400 watts per board under stress. That means every 100 trillion operations per second comes at a heavy energy cost when scaled across thousands of boards. LightGen hits 664 TOPS per watt because interference-based analog neural math loops waste far less energy to resistive heat than digital transistor switching does, but only for workloads in the chip's lane. Vision generative, analog friendly, and preset into its optical neurons. This does not mean the chip trains LLMs or replaces general GPUs universally. It means it runs preset neural vision generative math loops without fragmentation and without switching billions of digital gates per cycle. Another twist in this story is manufacturing. LightGen and Accel were both fabricated using deep ultraviolet immersion lithography, with multi-patterning rather than the highly restricted extreme ultraviolet scanners needed for the most advanced silicon nodes. EUV scanners operate at a 13.5 nanometer wavelength and are extremely expensive and tightly controlled. DUV immersion scanners operate at 193 nanometers, which normally means heavier multi-patterning to approach advanced digital transistor density. Photonics sidesteps that constraint not by printing smaller transistors, but by shifting the compute into the optical domain, where transistor switching density isn't the limiting factor for the specific workloads being tested. That doesn't make photonics easy. Manufacturing photonic neurons at wafer scale is brutally difficult. Photonic neurons compute through interface and resonance, and that means the optical alignment has to be near perfect at nanometer precision. Silicon is digital and clock-based. Photonic alignment is analog and wave-based. One misalignment can collapse the interface pattern and ruin the compute path. That's why LightGen remains a prototype, turning prototypes into production hardware with reliable yields, with integrated electro-optic I/O layers, with companion digital orchestration hubs. Those are the engineering challenges that stand between today's press release and tomorrow's data centers. And then there's the practical integration question. Even if LightGen computes 35,700 TOPS internally, AI data still enters and exits in digital form. Photonic chips need electro-optic conversion layers, calibration stacks, or companion hubs to manage data orchestration and decode optical latent outputs back into digital pipelines. In the LightGen design, the researchers intentionally kept compute and memory orchestration off the chip, letting a companion hub handle those functions while the photonic stack handles the heavy generative visual math loops. That design reduces power leakage and heat, but it raises the real question. How efficiently can the optical domain talk to the digital ecosystem without collapsing its gains? That's the unknown that matters most right now. Economics makes this story massive. Vision generative AI is expensive because GPUs burn megawatts and need huge cooling, not because the math is too hard. If photonics scales into real production, power-hungry workloads could move to light-based silicon accelerators, reshaping data centers, cutting energy costs, and changing who controls future AI compute. But none of this means Nvidia's GPUs are suddenly obsolete. Nvidia still owns the general-purpose AI training, programmable software stacks, memory-heavy transformer tasks, and digital compute that requires arbitrary kernel execution and large-scale VRAM addressing. But if photonic accelerators like LightGen and hybrid engines like Accel scale, they could redefine the economic floor of the workloads that eat the most electricity today. So, will China's photonic chip actually beat Nvidia? Or will it stay a lab monster that never survives the real world? Comment your take. And if you want the real story behind the world's fastest moving AI breakthroughs, make sure to like and subscribe to Evolving AI for daily coverage.